The ground at Norris Geyser Basin is too hot to walk on, not metaphorically, not as a figure of speech. Literally, the soil temperature in a section of the basin that was open to visitors 18 months ago has exceeded the boiling point of water at Yellowstone's altitude. The boardwalks are closed. The signs say thermal disturbance. The scientists say something else entirely. They say the heat is coming from below, not from the hydrothermal system, not from the superheated water that has circulated through Yellowstone's plumbing for centuries. From below the hydrothermal system, from the layer beneath the layer that powers the geysers and the hot springs and Old Faithful itself. From the magma. In the 6 weeks since we covered the April 2026 anomalous data, the deep seismic swarm, the accelerating ground deformation, the new thermal feature at Norris, every single monitoring parameter the Yellowstone Volcano Observatory tracks has moved in the same direction, not back toward baseline forward. The helium-3 signal in the gasochemistry data came back elevated. That is the fingerprint of mantle-derived gas. That is the chemical signature of material that originated not in the hydrothermal system, not in the circulating groundwater that most Yellowstone activity comes from, but in the magmatic system, in the partially molten rock sitting 5 to 17 kilometers below the surface of Wyoming. It is above it, and moving further above it rather than returning toward it. That is what justified the alert level change. Not a single dramatic event, not a precursory explosion, not a visible surface eruption. The slow, sustained, multi-parameter departure from everything the monitoring network has established as background behavior. The alert system exists for exactly this situation. For the moment when the accumulating evidence across independent monitoring streams reaches a threshold that formal institutional language is required to communicate. That threshold has been crossed. And the question that every volcanologist in the United States is asking right now, the question the data is forcing onto the table, whether the scientific community is ready to answer it or not, is which direction the system moves from here. Yellow is not the end of the scale. It is the second rung of a four-rung ladder. The rungs above it have names. And understanding what those names mean, what data would justify moving to them, is the only way to understand what we are actually watching. Was the April anomaly the beginning of a sequence that is now escalating? Or is yellow the ceiling, the point at which the system stabilizes and begins its long return to baseline? The instruments will tell us, and tonight, we start reading them. When we covered the April anomaly 6 weeks ago, one of the key pieces of data we said to watch for was the helium isotope ratio from the gas chemistry sampling that had been intensified at Norris Basin. That data is in. Helium comes in two stable isotopes, helium-3 and helium-4. The ratio between them, written as He, is one of the most diagnostic tools available in volcanology for tracing the origin of volcanic gases. Here is why. Helium-3 is primordial. It was produced in the first 3 minutes after the Big Bang, incorporated into the material that eventually formed the Earth, and has been slowly outgassing from the planet's interior ever since. The mantle is rich in helium-3. The crust is not. As primordial helium-3 is released from the mantle, it rises. As it moves through the crust toward the surface, it mixes with crustal helium-4, produced continuously by the radioactive decay of uranium and thorium in continental rocks. The ratio of helium-3 to helium-4 therefore tells you where a gas sample came from. A high ratio, close to the mantle value, means the gas originated deep in mantle-derived material. A low ratio, close to the crustal value, means the gas spent most of its journey in the crust, mixing with radiogenic helium-4, losing its mantle signature. At Yellowstone, the helium isotope ratios in hydrothermal gases have been measured for decades. The baseline ratio, the value changes to surrounding features and elevated ground temperatures. Steamboat entered a period of sporadic activity that continued through the 1970s and 1980s. In 2003, as mentioned in our previous coverage, Norris experienced the most significant thermal disturbance recorded in the modern monitoring era. A zone of the Tantalus Creek area registered ground temperatures high enough to melt road asphalt. Several new features appeared. Existing features changed character. The basin was partially closed to visitors. The disturbance resolved over approximately 8 months. In 2018, Steamboat Geyser entered a period of extraordinary activity, erupting 32 times that year after having been essentially dormant for 3 years. Scientists linked the activity to a hydrothermal disturbance in the Norris area that was accompanied by elevated seismicity and minor ground deformation. The episode resolved by 2021 as Steamboat's eruption frequency declined. Each of these episodes, and there are others in the record, represents a period when the Norris Basin was expressing elevated heat and fluid flux from below. Each of them resolved, none of them escalated to eruptive activity, but each of them was driven primarily by hydrothermal processes, changes in the circulation of superheated water through the existing plumbing system Changes in flow paths, pressure, and heat distribution within a system fundamentally driven by groundwater interacting with a deep heat source. The current episode is different in a way that has not characterized any of those previous disturbances. The helium signal is different. The 14.3 raw ratio does not appear in the records of previous Norris disturbances. The gas chemistry from the 2003 episode, the most severe in the modern monitoring era, remained consistent with hydrothermal sources throughout the disturbance. The depth of the seismicity is different. Previous Norris disturbances produced seismicity concentrated in the 2 to 8 kilometer range, the hydrothermal zone. The current swarm's deep component at 12 to 20 kilometers places it below the hydrothermal system entirely and within the zone of the magmatic reservoir. The focal mechanisms are different. The tensile failure signature in the deep events has not been reported in the analysis of previous Norris swarms. The current episode shares the surface expression of previous Norris disturbances. Elevated temperatures, new features, ground uplift, but the subsurface signals driving those surface expressions are qualitatively different from what has driven them before. That difference is what the alert level change is communicating. It is not communicating that Yellowstone is about to erupt. It is communicating that what is happening right now at Norris is not the same as what happened in 2003 or 2018 or any of the previous historical episodes. Something new is happening. And in a system as consequential as Yellowstone, new is a word that demands full attention. One of the most fundamental characteristics of the Yellowstone caldera is that it breathes. This is not a metaphor. The caldera floor literally rises and falls over years-long cycles, driven by using direct flux measurement. 340 tons per day localized to the Norris Basin alone. 340 tons per day from one area of one geyser basin, more than the previous total emission for the entire Yellowstone system. That number is not consistent with a hydrothermal source. The hydrothermal system does not produce 340 tons of sulfur dioxide per day. That number is consistent with a direct magmatic source, with gas exsolving from melt and finding a pathway to the surface without being fully scrubbed by the overlying water system. It means the pathway between the magmatic source and the surface is not just more permeable than before. It is sufficiently open that the scrubbing capacity of the hydrothermal system, the enormous buffering effect of millions of liters of circulating groundwater that normally absorbs magmatic gases, is being overwhelmed in the Norris area. More gas is coming up than the water can absorb. That is a fundamentally different statement about the state of the system than anything in the monitoring record. To put 340 tons per day in context, Mount St. Helens in the months before its 1980 eruption was emitting approximately 200 tons of sulfur dioxide per day. Pinatubo, in the weeks before its catastrophic 1991 eruption, was emitting 5,000 tons per day. The current Norris emissions during the 40 years of systematic monitoring. The 640 0-year gap is relevant for a different reason than the overdue narrative. It is relevant because it tells us something about the current state of the magmatic system after 640,000 years without a super eruption. The shallow magma reservoir is in a specific state. It has been accumulating heat and volatile pressure from the mantle plume for that entire period. It has been cycling through uplift and subsidence episodes, pressurizing, then partially releasing, then repressurizing. Each of those episodes has been resolved by one of two mechanisms. Either the pressure dissipated back into the system, or it was released through smaller eruptive events, lava flows, hydrothermal explosions. The system has not had a major pressure release in at least 70,000 years, the age of the last significant lava flow eruption. 640,000 years of input with only partial outputs. The pressure budget of the system is not zero. The volatile content of the melt is not empty. The system has been loading. What the current data might be showing is that after a period of loading that has no modern precedent in the monitoring record, the system has begun to express that loading in a new way, not through the hydrothermal system. That valve has been open for 640 zillion years and has not been sufficient to fully decompress the magmatic source. Through a new pathway, through the fractured zone above the magma reservoir at Norris, where the crust is thinnest, where the plumbing is most direct, through the crack in the road, through the new fumarole, through the helium-3 in the gas, through the centimeters of rising ground. The magma is not at the surface, but the pressure from the magma has found a new way to speak, and it is speaking in a language the monitoring network has not heard before. Alert level orange at Yellowstone would represent the most significant formal volcanic hazard designation in American history. No volcano in the contiguous United States has been at orange for longer than a few months. In those instances, Mount St. Helens in the periods leading to its 2004-2008 dome-building eruption involved a system with a very different geometry and a much shallower magmatic source. Orange means eruption is considered foreseeable if trends continue. It means that the monitoring data has crossed multiple thresholds. It means that the probability of eruptive activity in the near term is considered significant enough that formal emergency management protocols are activated. For Yellowstone specifically, an orange designation would trigger a cascade of formal responses. The National Park Service would begin evacuation of the park. At peak season, Yellowstone hosts approximately 30,000 visitors per day. An ordered evacuation of the park could be accomplished in approximately 8 to 12 hours under good conditions. The surrounding gateway communities, West Yellowstone, Gardner, Cook City, Jackson, would be included in the evacuation advisory. FEMA would activate pre-positioned response assets for the broader Yellowstone region. The FAA would impose flight restrictions over the Caldera area, consistent with the Aviation Color Code Orange designation that accompanies the ground alert. The NRC, the Nuclear Regulatory Commission, would conduct precautionary assessments of the potential impact of elevated seismicity on nuclear facilities within a 1,000-kilometer radius. None of these responses have been activated. None of them are imminent based on the current yellow designation. But they exist, they are planned, they have been rehearsed, and the fact that they are planned tells you something important about how seriously the relevant agencies take the low probability, high consequence end of the Yellowstone's risk distribution. The gap between yellow and orange is defined by the three thresholds I described earlier. The current data is below all three thresholds. For orange to be declared, the monitoring network would need to show one or more of sustained caldera-wide deformation approaching 10 centimeters per month, sustained shallow seismicity above magnitude 3 for more than 72 hours, or a system-wide sulfur dioxide flux approaching 1,000 tons per day. Those are not trivial thresholds. They represent a substantial escalation above current conditions. But they are thresholds that the reservoir had migrated into a previously unmapped pocket of partial melt closer to the surface than the main reservoir, a magmatic outpost, as it were, extending the reach of the magmatic system upward beneath Norris. The paper received modest attention at the time. It was cited in subsequent tomography studies. Its implications were discussed in the volcanological community, but it was not widely treated as a finding that changed the understanding of near-term Yellowstone hazard. Because in 2011, the surface data at Norris was not showing any of the signals that are showing now. 13 years later, those signals have arrived, and the zone of low seismic velocity that the 2011 paper identified, the partial melt pocket at 8 to 14 kilometers depth, sits directly within the depth range of the tensile failure events in the April swarm. It sits directly below the accelerating surface deformation. It sits directly below the new fumarole. The paper was describing what was already there. The current data is describing what that pre-existing feature is now doing. The scientists who wrote that paper were right. The partial melt is there. It was always there. What is new is not its existence. What is new is its behavior. Something has changed in the magmatic system that is causing that pocket of partial melt to interact more actively with the overlying crust than it has in the monitoring period. The pressure from below, from the main magma reservoir, and from the mantle plume beneath it, has changed in a way that is pushing the Norris partial melt zone into a more active state. The observatory is now conducting an updated seismic tomography analysis using the April swarm data to produce a new higher resolution image of the crustal structure beneath Norris.